Empty space isn't empty. For decades, astronomers mapped the universe and found something unsettling: vast regions where almost nothing exists. These cosmic voids stretch hundreds of millions of light-years across, containing so few galaxies that they seemed like holes punched through reality itself. Scientists assumed these voids were mostly vacant, relics of the universe's earliest moments when matter clumped together, leaving empty pockets behind. But when researchers pointed their most powerful instruments into these supposedly barren regions, they discovered something that shouldn't be there. Hidden inside the deepest voids, invisible to ordinary telescopes, lies a network of structures that challenges everything we thought we knew about cosmic emptiness. Faint filaments of gas, rogue galaxies moving at inexplicable speeds, and mysterious dark matter concentrations populate these seemingly dead zones. The void, it turns out, is anything but empty, and what we're finding there is rewriting the story of how the universe evolved, the architecture of cosmic emptiness. When astronomers first mapped the large-scale structure of the universe in the 1,970 seconds and 1,980 seconds, they expected to find galaxies distributed relatively evenly throughout space. Instead, they discovered something far stranger. Galaxies cluster together along vast filaments and walls, surrounding enormous spherical regions almost devoid of matter. These cosmic voids represent the largest structures in the known universe, with some spanning over 300 million light-years in diameter. The Botes void, discovered in 1981, contains only 60 galaxies in a region where thousands should exist based on the cosmic average. The supervoid in Eridanus stretches nearly 1 billion light-years across, creating a cold spot in the cosmic microwave background radiation. These voids form a kind of cosmic skeleton, defining the negative space between the bright filaments where galaxies congregate. The distribution follows a pattern astronomers call the cosmic web, a vast network where matter concentrates along strands and nodes, leaving bubble-like voids in between. Early computer simulations of cosmic evolution predicted this structure, showing how tiny density fluctuations in the early universe would amplify over billions of years. Denser regions attracted more matter through gravity, growing into galaxy clusters and filaments. Meanwhile, underdense regions expanded faster than average, evacuating their matter into surrounding walls and becoming increasingly empty. For decades, researchers assumed these voids were relatively simple structures, just regions where matter happened to be scarce. The formation process seemed straightforward. As the universe expanded after the Big Bang, quantum fluctuations created slight variations in density. Gravity amplified these differences, pulling matter from underdense regions into overdense ones. Over billions of years, this process carved out the cosmic web we observe today, with voids as the empty spaces left behind. Yet closer examination revealed unexpected complexity. Voids aren't perfectly spherical or uniformly empty. They have internal structure, with mini-filaments and small galaxy groups sometimes suspended inside them like islands in an ocean. Their shapes are irregular, often elongated or compressed where they meet neighbouring voids or filament walls. Some voids appear to be expanding faster than the universe's average expansion rate, pushed outward by the mysterious force of dark energy. The boundaries aren't sharp edges, but gradual transitions where density slowly increases toward the surrounding walls. The distribution of voids themselves follows patterns. They tend to be roughly the same size, typically between 100 and 300 million light-years across, suggesting some universal process governs their formation. Smaller voids are rarer, perhaps because they haven't had time to fully evacuate or because they've merged with larger neighbours. Giant voids like the Eridanus supervoid are also uncommon, representing statistical outliers in the cosmic distribution. This size clustering hints at fundamental physical processes operating during the universe's youth, when the seeds of structure first formed. Mapping these voids requires enormous surveys covering vast volumes of space. Projects like the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey measured the positions and distances of millions of galaxies, creating three-dimensional maps of cosmic structure. When researchers identified voids in these maps, they used sophisticated algorithms to define boundaries and measure properties like volume, shape, and emptiness. The results showed that voids occupy roughly 80% of the universe's volume, despite containing less than 10% of its galaxies. The formation timeline of voids stretches back nearly to the Big Bang itself. Tiny quantum fluctuations during the inflationary epoch, a brief period of exponential expansion in the universe's first fraction of a second, created the initial density variations. By the time the universe was 380,000 years old and released the cosmic microwave background radiation, these fluctuations had grown into distinct hot and cold spots in the primordial plasma. Over the following hundreds of millions of years, gravity sculpted these variations into the first generation of voids and filaments. As galaxies formed and evolved, they continued draining matter from void interiors, making them progressively emptier. Supernovae and stellar winds from early star formation added energy to the gas, heating it and driving it outward from underdense regions toward denser areas where gravity was stronger. This feedback process accelerated void expansion, hollowing them out more efficiently than gravity alone could accomplish. By the time the universe reached half its current age, the cosmic web had assumed its modern appearance, with well-defined voids separated by dense walls and filaments. Modern observations have revealed subtle variations in void properties that encode information about cosmic history. Some voids show evidence of ancient galaxy groups that once occupied their centers but have since drained away, leaving only faint traces. Others contain unexpected concentrations of dark matter detected through gravitational lensing, the bending of light from distant galaxies passing through the void. These dark matter clumps exist without accompanying visible galaxies, suggesting complex interactions between ordinary and dark matter during void formation. The edges of voids where they meet the surrounding cosmic web are particularly interesting. Here, galaxies experience unique environmental conditions, with lower density on one side and higher density on the other. Studies show that galaxies in void walls often have higher star formation rates than those in dense clusters, possibly because they retain more gas that hasn't been stripped away by interactions with neighbouring galaxies. The walls themselves can be quite thin, sometimes only 10 or 20 million light-years thick, creating sharp transitions between void interiors and the surrounding cosmic web. The hunt for void galaxies. Within the apparently empty expanses of cosmic voids, astronomers have discovered something unexpected: galaxies. These void galaxies represent a peculiar population existing in one of the universe's most isolated environments. Finding them requires dedicated surveys using sensitive instruments capable of detecting extremely faint objects against the darkness of space. The challenge is significant. Void galaxies are often small, dim, and widely scattered, making them difficult to identify even with powerful telescopes. The first systematic searches for void galaxies began in the 1,990 seconds following the discovery of large voids in galaxy redshift surveys. Astronomers reasoned that while voids are underdense compared to the cosmic average, they shouldn't be completely empty. Gravitational physics predicts that some matter should remain, forming small halos capable of hosting dwarf galaxies. Early surveys confirmed this prediction, finding scattered dwarf galaxies within void interiors, though far fewer than in denser regions. These void galaxies exhibit distinctive characteristics that set them apart from their counterparts in normal environments. Most are dwarf or irregular galaxies, lacking the grand spiral structures or massive elliptical shapes common in galaxy clusters. Their stellar populations tend to be younger on average, with ongoing star formation creating bright blue stars that dominate their light output. This active star formation suggests void galaxies retain more gas than similar mass galaxies in denser environments, where interactions and environmental processes strip away star-forming material. Spectroscopic observations reveal additional peculiarities. Void galaxies often show lower metallicities, fewer heavy elements, like carbon, nitrogen, and oxygen, compared to galaxies of similar mass in denser regions. This chemical deficit indicates they've experienced less stellar recycling over cosmic time. In normal environments, successive generations of stars produce heavy elements that enrich the interstellar medium. When these stars die in supernovae, they release these elements into space, where they're incorporated into new stars and planets. Void galaxies, isolated from the galactic mergers and gas flows common in dense regions, evolve more slowly, retaining a more primitive chemical composition. The spatial distribution of void galaxies provides clues about void structure and evolution. Rather than being randomly scattered, void galaxies tend to concentrate along faint filaments within void interiors, mini versions of the cosmic web existing inside the larger voids. These internal filaments suggest that voids have hierarchical structure, with smaller scale patterns nested within the larger emptiness. Some researchers propose that voids are themselves composed of smaller subvoids, creating a fractal-like distribution of matter across multiple scales. Measurements of void galaxy velocities reveal another surprise. Many are moving unusually fast relative to the cosmic expansion. In normal regions, galaxies' peculiar velocities, their motion relative to the Hubble flow, typically range from a few hundred to perhaps 1,000 kilometers per second, driven by gravitational attraction to nearby massive structures. But some void galaxies show peculiar velocities exceeding 1,500 kilometers per second, far higher than expected given the low matter density in their surroundings. This excess velocity might indicate they're falling toward distant massive structures outside the void, or perhaps responding to dark matter concentrations that aren't traced by visible galaxies. The evolution of void galaxies differs markedly from galaxies in denser environments. In galaxy clusters, interactions are common. Galaxies collide, merge, and strip gas from each other through gravitational tides and ram pressure. These violent processes transform spiral galaxies into ellipticals, quench star formation, and redistribute stars into diffuse halos. Void galaxies, by contrast, experience few, if any, interactions over billions of years. They evolve in relative isolation, maintaining their gas reservoirs and forming stars at steady rates, determined primarily by internal processes rather than external disturbances. This isolation makes void galaxies valuable laboratories for studying galaxy evolution. By comparing void galaxies to similar mass galaxies in denser regions, astronomers can isolate the effects of the environment from those of mass and internal physics. Recent studies suggest that the environment plays a stronger role than previously thought in shaping galaxy properties. Spiral galaxies in voids tend to have more extended gas disks, higher gas fractions, and bluer colours than their counterparts in clusters, indicating that the absence of environmental harassment allows them to continue forming stars efficiently. Some void galaxies show evidence of past interactions despite their current isolation. Tidal tails, elongated streams of stars and gas pulled out by gravitational forces during close encounters, appear in deep images of certain void systems. These features suggest that void galaxies weren't always so isolated. In the past, when the universe was younger and denser, interactions may have been more common even in void interiors. As the universe expanded and voids grew, these galaxies became increasingly isolated, preserving fossil evidence of their more active past. The dark matter halos hosting void galaxies present additional puzzles. Simulations of cosmic structure formation predict that dark matter should form halos of various masses throughout the universe, including in void interiors. Yet, the number of observed void galaxies falls short of simulation predictions by significant factors. This discrepancy, called the void phenomenon, might indicate that galaxy formation is suppressed in underdense regions. Perhaps small dark matter halos in voids struggle to accumulate and retain enough gas to form stars. Alternatively, many predicted halos might exist but remain dark, failing to form luminous galaxies for reasons astronomers are still investigating. Dark matter in the void. The conventional picture of cosmic voids as nearly empty regions applies only to ordinary matter, the atoms and molecules that make up stars, planets, and gas clouds. Dark matter, the invisible substance comprising roughly 85% of all matter in the universe, tells a different story. Theoretical models and indirect observations suggest that dark matter persists in void interiors, forming a diffuse network that underpins void structure even where few or no galaxies exist. Understanding dark matter's distribution in voids has become crucial for testing cosmological models and theories of structure formation. Dark matter's presence in voids can't be detected directly because it doesn't emit, absorb, or scatter light. Instead, astronomers rely on gravitational effects. One powerful technique is gravitational lensing, where massive objects bend light from more distant sources. Strong lensing produces dramatic multiple images of background galaxies, but requires massive foreground structures like galaxy clusters. Weak lensing creates subtler distortions, stretching background galaxy images by tiny amounts, detectable only through statistical analysis of thousands of galaxies. Applying weak lensing to cosmic voids presents technical challenges. The signal is inherently weak because voids contain less mass than typical regions. Detecting this faint signal requires extremely precise shape measurements of background galaxies and sophisticated statistical methods to separate lensing effects from intrinsic galaxy shapes and measurement noise. Despite these difficulties, several surveys have successfully measured weak lensing by voids, confirming that dark matter does indeed exist in void interiors, though at lower density than surrounding regions. The measured dark matter distribution in voids matches predictions from cosmological simulations reasonably well. These simulations, which model the evolution of dark matter from shortly after the Big Bang to the present day, show that voids aren't completely empty of dark matter. Instead, they contain perhaps 10 to 30% of the average cosmic dark matter density. This residual dark matter forms a web-like pattern within voids, faint filaments and small halos that don't contain enough matter to host luminous galaxies but still exert gravitational influence. Some simulations predict that voids should contain numerous small dark matter halos, gravitationally bound clumps with masses equivalent to dwarf galaxies or even smaller. These mini halos might number in the thousands within a single large void. Yet optical surveys find far fewer dwarf galaxies than predicted halos, suggesting that many dark matter halos remain dark, never forming stars. Several mechanisms could explain this galaxy formation suppression in voids. The lower overall density means less gas is available to cool and condense into stars. Small halos have weak gravity, making it harder to retain gas that's heated by stellar feedback or cosmic reionization. Without nearby massive galaxies to supply fresh gas through inflows, void halos might simply never accumulate enough material to sustain star formation. Recent radio surveys searching for neutral hydrogen gas in voids have found intriguing hints of this dark matter network. By mapping cold hydrogen at 21 centimeter wavelength, a transition that allows detection of neutral gas throughout the universe, astronomers have identified faint filamentary structures within void interiors. Some of these hydrogen filaments appear to connect isolated void galaxies, suggesting they trace dark matter filaments that channel gas through the void. Other hydrogen detections show gas clouds with no associated optical galaxies, potentially dark galaxies, where gas accumulated in dark matter halos but never formed enough stars to be visible. The velocity field within voids the pattern of how galaxies and gas move relative to the cosmic expansion, provides additional constraints on dark matter distribution. In regions where dark matter is denser, its gravity accelerates nearby objects, creating peculiar velocities that deviate from the smooth Hubble expansion. By measuring these velocity perturbations for galaxies around and within voids, astronomers can infer the dark matter distribution responsible. Results indicate that matter is flowing outward from void centers toward the surrounding walls, consistent with models where voids expand over time as their interiors become increasingly underdense. One of the most sensitive probes of void dark matter comes from studying the integrated Sachs-Wolf effect in the cosmic microwave background radiation. Photons from the CMB ancient light, released 380,000 years after the Big Bang, travel through the universe's evolving gravitational field on their way to Earth. When photons pass through a void, they gain energy climbing out of its gravitational potential well. If the universe was static, this energy gain would be exactly cancelled by the energy lost falling in. But because the universe is expanding and voids are growing deeper over time, the cancellation is imperfect, leaving a net energy shift that slightly heats the CMB photons passing through voids. This heating effect, though tiny temperature changes of only a few microkelvin, has been detected by comparing CMB maps with void catalogues from galaxy surveys. The measurements confirm that voids create cold spots in the CMB due to the integrated Sachs-Wolf effect, and the magnitude of these temperature decrements depends on the total matter content of voids, including dark matter. By precisely measuring these temperature shifts, astronomers can constrain how much dark matter resides in void interiors and how fast voids are expanding, both key tests of cosmological models. Simulations exploring different dark matter properties show that void structure depends sensitively on dark matter's nature. In the standard cold dark matter model, where dark matter particles move slowly and can clump on small scales, voids develop the hierarchical structure with numerous mini-halos. But in alternative models like warm dark matter, where particles move faster and can't form small halos, as easily void interiors would be smoother with fewer small-scale structures. By carefully measuring void properties and comparing them to predictions from different dark matter models, astronomers can test fundamental assumptions about what dark matter actually is. Recent surveys using gravitational lensing have even detected what appear to be dark matter islands within voids localized over densities with no associated visible galaxies. These features, if confirmed, could represent rare, massive dark matter halos that failed to form stars, or perhaps their statistical fluctuations in the dark matter distribution. Either way, their existence demonstrates that void interiors have complex dark matter structures not fully captured by simple empty space models. The interaction between dark energy and dark matter in voids provides another research frontier. Dark energy, the mysterious force accelerating the universe's expansion, should have its strongest effects in underdense regions like voids. Some modified gravity theories propose that dark energy behaves differently in low-density environments, potentially creating observable signatures in void expansion rates or dark matter distributions. By precisely measuring void properties and comparing them across cosmic time, looking at nearby voids versus distant ones, seen as they were billions of years ago, astronomers can test whether dark energy's strength varies with density, or epoch, the temperature structure of cosmic voids. Temperature might seem like an irrelevant property in the near vacuum of cosmic voids, but the tenuous gas that does exist there reveals crucial information about void evolution and the universe's thermal history. This gas, primarily hydrogen and helium left over from the Big Bang, exists at incredibly low densities, sometimes less than 1 atom per cubic meter. Despite being so sparse, its temperature carries signatures of the energetic processes that shaped cosmic structure, from the radiation released by the first stars to shocks driven by void expansion. Measuring void temperatures requires sophisticated techniques because the gas is too diffuse to emit detectable light on its own. Instead, astronomers use background sources, distant quasars, whose light passes through void regions on its way to Earth. As quasar light travels through the void, it interacts with any intervening gas through absorption. Hydrogen atoms absorb specific wavelengths corresponding to their electronic transitions, creating absorption lines in the quasar spectrum. The width of these absorption lines encodes information about gas temperature. Hotter gas has atoms moving faster, which Doppler broadens the absorption features. Analysis of quasar absorption spectra reveals that void gas temperatures typically range from 10,000 to 30,000 Kelvin, far hotter than interstellar gas in galaxies, but much cooler than gas in galaxy clusters. This temperature regime reflects the balance between heating processes that inject energy and cooling processes that radiate it away. The primary heating source is photoionization. Ultraviolet radiation from stars and quasars ionizes hydrogen atoms, converting their electron binding energy into kinetic energy that heats the gas. Once ionized, the gas cools primarily through free emission and recombination radiation, processes that become more efficient at higher densities. Temperature maps constructed from multiple quasar sightlines show that void interiors aren't uniformly heated. Instead, they exhibit temperature variations correlating with density structure. Regions along filaments within voids tend to be slightly warmer than the emptiest regions, likely because higher gas densities there intercept more ionizing radiation. The coldest gas appears in the centers of the largest voids, where densities are lowest and radiation fields weakest. These temperature gradients, though subtle, typically only a few thousand Kelvin, trace the three-dimensional structure of matter distribution within voids. The evolution of void gas temperatures over cosmic history provides insights into the universe's reionization epoch. In the early universe, hydrogen was neutral, making the cosmos largely opaque to ultraviolet light. Between about 400 million and 1 billion years after the Big Bang, the first stars and galaxies produced enough ionizing radiation to reionize the universe, converting neutral hydrogen back into ions and free electrons. This reionization process dramatically heated intergalactic gas, raising temperatures from a few hundred Kelvin in the neutral phase to 10,000 Kelvin or more once ionized. Observations of high redshift quasar spectra, looking at gas as it existed billions of years ago, show this thermal history encoded in absorption line properties. Shortly after reionization, void gas was relatively hot and uniform in temperature, reflecting recent photoionization heating. Over time, as the universe continued expanding and cooling, temperature fluctuations developed. Overdense regions stayed warmer due to continued heating from star formation and gravitational compression, while underdense, void regions cooled faster. By the present epoch, this process has created the temperature variations observed today, with voids containing the coolest intergalactic gas. Some theoretical models predict even more dramatic temperature structure in voids. If reionization occurred in an inhomogeneous manner, with some regions ionizing earlier than others, then relict, cold patches of gas might have survived in the deepest voids. These cold flows would represent the last reservoirs of gas that escaped reionization heating, remaining at temperatures of only a few thousand Kelvin. Detecting such cold gas would provide crucial constraints on how reionization proceeded and whether it truly ionized the universe uniformly. Shocks provide another source of void heating. As voids expand, their boundaries sweep through the surrounding cosmic web, driving shocks into the gas. These shocks convert the kinetic energy of expansion into thermal energy, heating the gas to temperatures potentially exceeding 100,000 Kelvin in the densest void walls. Simulations show that shock heating should create hot shells around void peripheries, with temperatures declining toward void interiors. X-ray observations targeting void regions have found tentative evidence for this predicted hot gas, though signals remain marginal and challenging to confirm. The metal content of void gas, trace amounts of elements heavier than helium, offers additional temperature diagnostics. Metals are produced by stellar nucleosynthesis and distributed through the intergalactic medium by galactic winds and supernovae. Even in voids, where galaxies are scarce, low levels of metal enrichment appear in quasar absorption spectra. The ionization states of these metals depend on both the intensity of ionizing radiation and gas temperature, allowing astronomers to break degeneracies in their measurements and constrain void temperatures more precisely. Cooling processes in voids operate differently than in denser regions. At cosmic average densities, radiative cooling times are comparable to or shorter than the universe's age, allowing gas to cool efficiently and condense into galaxies. But in void interiors, densities are so low that cooling times exceed the age of the universe by factors of 10 or more. This means void gas cannot cool and collapse into stars. It remains in a hot, diffuse phase, unable to form the dense clouds necessary for star formation. This cooling barrier explains why void interiors contain so few galaxies despite having substantial gas mass. Magnetic fields, threading the emptiness. Magnetic fields permeate the cosmos, from planetary interiors to galactic halos, but their presence in cosmic voids, the universe's most underdense regions, remained uncertain for decades. These fields, though weak compared to laboratory magnets or even Earth's field, play important roles in cosmic physics, affecting how charged particles move and how gas behaves. Recent observations suggest that magnetic fields do indeed exist in voids, raising questions about their origin and implications for our understanding of cosmic structure. Detecting magnetic fields in voids presents immense technical challenges. The primary method uses Faraday rotation, where polarized light from distant radio sources rotates as it passes through magnetized plasma. The rotation angle depends on both magnetic field strength and electron density along the line of sight. In voids, where electron densities are extremely low, the Faraday rotation signal becomes almost imperceptible. Yet advanced radio telescopes with exquisite sensitivity have begun detecting these subtle signatures, revealing magnetic fields in void regions. The measured field strengths are remarkably weak, typically around 10, -16 to 10, -15 Gauss, roughly 1,000,000 times weaker than Earth's magnetic field and thousands of times weaker than fields in galaxy clusters. Despite their weakness, these fields pervade enormous volumes, meaning they contain significant total magnetic energy. The fields appear organized into coherent structures stretching across millions of light years, suggesting they trace the faint filamentary network within void interiors rather than existing as random fluctuations. The origin of void magnetic fields remains debated. In galaxy clusters and filaments, magnetic fields are thought to arise from seed fields generated in the early universe and then amplified by turbulence and gravitational collapse. As matter clumps under gravity, it drags magnetic field lines along, compressing and intensifying them. But voids lack the density contrast and turbulent motions needed for this amplification mechanism to operate efficiently. So how did magnetic fields in voids form? One possibility is that void magnetic fields represent primordial relic seeds generated in the very early universe that have survived largely unamplified to the present day. Several early universe mechanisms could have produced such seeds. Phase transitions, as the universe cooled, might have generated fields through symmetry breaking. Alternatively, fluctuations during cosmic inflation could have created electromagnetic inhomogeneities alongside the density fluctuations that seeded structure formation. If void fields are indeed primordial, their strength and structure would provide unique constraints on physics in the first moments after the Big Bang. Another scenario invokes outflows from galaxies as field sources. Galactic winds driven by supernovae and active galactic nuclei carry magnetized gas out of galaxies and into the surrounding intergalactic medium. Some of this ejected material could reach void regions, particularly if outflows occurred early in cosmic history when voids were smaller and less evacuated. Computer simulations testing this idea show that galaxy-driven magnetization can produce field strengths and coherence lengths roughly consistent with observations, though whether enough magnetized gas reaches deep void interiors remains uncertain. A third possibility involves cosmic ray streaming. Cosmic rays, high-energy particles produced by supernovae and other energetic events, can escape galaxies and propagate through intergalactic space. As they stream through plasma, they generate instabilities that amplify magnetic fields. This process might operate even in void environments, though the low particle densities would make it slow and inefficient. Recent theoretical work suggests that cosmic ray-driven magnetization could produce the weak fields observed in voids over cosmic timescales. The structure of void magnetic fields offers clues to their origins. If fields are primordial, they should be relatively smooth and uniform, lacking the tangled complexity seen in galaxy clusters, where turbulence has scrambled field configurations. Observations hint that void fields may indeed be more ordered, with coherent orientations extending across large scales. This ordering could reflect the field's primordial origin, or perhaps the gentle shearing motions as voids expand, which might align field lines into organized patterns. Void magnetic fields, weak as they are, affect cosmic ray propagation. charged particles spiral along magnetic field lines, their paths confined by the fields even in near-empty space. Cosmic rays entering voids from surrounding filaments would be channeled and scattered by void fields, affecting their energy spectrum and arrival directions. By studying cosmic ray properties measured both at Earth and by space-based detectors, astronomers can indirectly probe magnetic field structure in voids and other low-density regions. The fields also influence how gas moves in voids. Magnetized gas develops pressure support from magnetic tension, which resists compression perpendicular to field lines. Though this magnetic pressure is negligible compared to gravitational forces in high-density regions, it might matter in void environments where all forces are weak. Simulations including magnetic fields show subtle differences in void structure compared to non-magnetic models, suggesting that fields play a small but measurable role in void evolution. One of the most intriguing implications concerns dark matter. Certain dark matter candidates, particularly ultralight axions, could interact with magnetic fields through quantum mechanical effects. These interactions might be detectable in regions where environmental noise is minimized, precisely the conditions found in cosmic voids. By precisely measuring magnetic field properties in voids and comparing them to theoretical predictions for different dark matter models, astronomers might be able to constrain or even identify dark matter's nature through its electromagnetic signatures, the motion of void walls. Cosmic voids don't remain static. They evolve as the universe expands, their boundaries moving outward as matter continues flowing into surrounding filaments and walls. This motion, though imperceptibly slow on human timescales, becomes significant over millions and billions of years, reshaping cosmic structure and providing crucial tests of cosmological models. By tracking how void walls move, astronomers can measure the universe's expansion history and constrain dark energy's properties. The outward expansion of voids occurs because their interiors are underdense compared to the cosmic average. In general relativity, underdense regions create gravitational potential wells with negative depth. They push rather than pull. This repulsive gravity accelerates matter away from void centers toward higher density surroundings. Combined with the universe's overall expansion, this effect causes void radii to grow faster than the cosmic scale factor, making them progressively emptier over time. Measuring void expansion requires tracking the positions of galaxies, defining void boundaries over time. This is challenging because cosmic expansion itself carries galaxies apart, and disentangling void-specific expansion from the background Hubble flow requires extremely precise distance measurements and careful modelling. Early attempts used statistical methods comparing void sizes at different cosmic epochs by analysing galaxy surveys at various redshifts. Results showed that voids were indeed expanding, with their growth rate exceeding expectations from simple models. More recent work uses individual galaxy velocities to directly measure void wall motion. By combining galaxy positions from optical surveys with velocity measurements from spectroscopy, astronomers can construct maps showing how galaxies move relative to the average cosmic expansion. Galaxies on void edges show systematic outward motions, flowing away from void centers at speeds of a few hundred kilometers per second. These velocity flows trace the gravitational influence of the void's underdensity, confirming theoretical predictions and providing quantitative measurements of void expansion rates. The dynamics of void expansion depend sensitively on the universe's matter and energy content. In a matter-dominated universe, void expansion would gradually slow as gravitational attraction from surrounding overdensities pulls back on escaping matter. But In a universe dominated by dark energy, as observations indicate our universe, is void expansion can accelerate over time. Dark energy's repulsive gravity enhances the effect of voids' negative gravitational potential, causing them to expand faster than they would in a matter-only model. This makes void expansion an independent probe of dark energy. By measuring how void sizes evolve with cosmic time and comparing these measurements to predictions from different cosmological models, astronomers can constrain dark energy's equation of state, the relationship between its pressure and density that determines its gravitational effects. Early results from void expansion studies favor a cosmological constant consistent with other dark energy probes, though uncertainties remain large enough to allow for more exotic models. Void wall velocities also encode information about gravitational physics. In Einstein's general relativity, the relationship between matter distribution and velocity flows is precisely specified. Alternative theories of gravity modifications propose to explain cosmic acceleration without invoking dark energy predict different relationships. Some modified gravity theories, for instance, would cause void walls to move faster or slower than general relativity predicts for the same matter distribution. By carefully measuring void wall velocities and comparing them to matter density maps from galaxy surveys and weak lensing, astronomers can test whether gravity behaves as Einstein predicted on the largest cosmic scales. The interaction between neighboring voids adds complexity to expansion dynamics. When voids' boundaries approach each other, their expansion can slow as the intervening wall of matter resists compression. Eventually, voids can merge, their boundaries dissolving as they form a single, larger void. Simulations show that void mergers are common, occurring throughout cosmic history and helping to build the largest voids we observe. Identifying merging voids in observational data provides stringent tests of structure formation models and void evolution theories. Some voids show asymmetric expansion, growing faster in some directions than others. This asymmetry likely reflects anisotropies in the surrounding matter distribution voids expand more easily toward regions that are already underdense and less easily toward massive clusters or filaments. Measuring void shapes and how they evolve provides information about tidal gravitational fields in the cosmic web, which in turn constrain large-scale velocity flows and mass distributions. The smallest voids face competition between expansion and collapse. If a small, underdense region is surrounded by significant overdensities, the inward gravitational pull from its surroundings might overcome the outward push from its own underdensity, causing it to collapse and fill in rather than expand into a mature void. This process, called void collapse, might explain why very small voids are relatively rare. In surveys, those that tried to form were crushed by surrounding structure before they could grow. Conversely, the largest voids seem to be expanding most vigorously. Observations show that supervoids, the rare voids exceeding 300 million light-years in diameter, have faster than average expansion rates and more coherent outflow patterns. This could indicate they formed from especially significant underdensities in the early universe, or that their large size allows them to expand more freely without interference from surrounding structures. Ancient light passing through nothing. Every photon of light travelling across the universe carries information about what it encountered along its journey. When that journey passes through cosmic voids, subtle imprints accumulate on the light, faint signatures that reveal void properties and test fundamental physics. By analysing these imprints across millions of light paths, astronomers transform voids from empty nuisances into valuable cosmic laboratories. The cosmic microwave background radiation provides the oldest light available photons that have travelled for 13.8 billion years since their release, 380,000 years after the Big Bang. As CMB photons traverse the universe, they pass through evolving structures, including cosmic voids. When photons enter a void, they climb out of its gravitational potential well, losing energy in the process. If the universe were static, photons would regain this energy as they exit the void, climbing back up the potential. But because the universe expands and voids grow deeper over time, photons don't fully recover the lost energy. They emerge slightly redshifted and cooler than when they entered. This integrated Sachs-Wolf effect creates cold spots in the CMB where light has passed through voids. The temperature decrements are tiny, typically a few microkelvin against the CMB's 2.7 Kelvin background, but detectable with sensitive instruments like the Planck satellite. By cross-correlating CMB temperature maps with void catalogues from Galaxy surveys, astronomers have confirmed these cold spots exist where voids lie along the line of sight. The measured temperature shifts match predictions from cosmological models, providing independent confirmation of dark energy's influence on cosmic structure evolution. Some researchers have identified anomalously large cold spots in the CMB that might be associated with exceptionally large voids or supervoids. The most famous is the CMB cold spot in the constellation Eridanus, a region about 10 degrees across where temperatures are roughly 70 microkelvin colder than surrounding areas. Galaxy surveys have found an enormous void along the same line of sight to the Eridanus supervoid, stretching nearly 1 billion light-years. Whether this supervoid can fully explain the cold spot's temperature remains debated, with some studies suggesting the void is too small or too distant to produce the observed effect. Alternative explanations, ranging from statistical flukes to exotic physics, have been proposed, making the cold spot one of cosmology's enduring mysteries. Quasar light provides another probe of void properties across cosmic time. Quasars are extremely luminous galactic nuclei powered by supermassive black holes. Because they're so bright, they can be detected at enormous distances, with light from the most distant quasars travelling over 13 billion years to reach us. As quasar light crosses the universe, it passes through numerous voids at different epochs, each leaving spectroscopic signatures. The most prominent signature is the Lyman alpha forest, a series of absorption lines created when intervening hydrogen gas absorbs quasar light at the Lyman alpha wavelength. Dense regions produce strong, broad absorption features, while underdense void regions produce weaker, narrower lines or no absorption at all. By analysing the statistical properties of Lyman alpha forests across many quasars, astronomers can reconstruct the density distribution of hydrogen along each line of sight, effectively creating one-dimensional maps of matter distribution, including voids. These Lyman alpha measurements reveal void evolution over cosmic history. At high redshifts looking back 10 or 11 billion years, voids were smaller and less empty than today. The absorption forests show more continuous absorption, with fewer completely transparent regions, indicating that matter was more uniformly distributed. As time progressed and the universe expanded, voids grew larger and emptier, creating increasingly long gaps in the Lyman alpha forest, where essentially no hydrogen exists to absorb quasar light. Temperature information also hides in Lyman alpha forests. The width of absorption lines depends on gas temperature. Hotter gas has faster moving atoms that Doppler broaden the lines. By carefully modelling line shapes, astronomers extract temperature measurements for intergalactic gas at various densities, including void regions. Results show that void gas is cooler than average, confirming expectations that low-density regions cool more efficiently than dense ones where gravitational heating and feedback processes dominate. Rare absorption systems, called metal lines, provide additional void diagnostics. Metals elements heavier than helium are produced in stars and distributed through the intergalactic medium by galactic outflows. Even in voids, low levels of metal enrichment appear, detectable through absorption features from carbon, silicon, oxygen, and other elements. The presence of metals in voids indicates that galactic winds have reached these regions, carrying processed material far from their parent galaxies. The metal abundance patterns constrain how much stellar feedback has occurred and how efficiently winds propagate through low-density environments. Gravitational lensing of distant quasars by foreground voids provides another light-based probe. Though voids have negative gravitational potential and thus can't focus light like massive clusters, they create subtle magnification patterns, expanding the apparent size of background sources while dimming them proportionally. This effect, called de-amplification, is challenging to detect but has been measured statistically for quasars behind known voids. The magnification signal depends on void mass and density profile, offering yet another way to map void properties. One emerging application uses fast radio bursts, brief, intense pulses of radio waves from distant galaxies to probe void structure. These millisecond duration bursts propagate through the intergalactic medium, their signals dispersed by free electrons along the line of sight. By measuring this dispersion and comparing it to the expected contribution from known matter distributions, astronomers can infer the presence of unseen material, including dark matter and hot gas in voids. Early results suggest fast radio burst dispersion measurements might reveal hidden baryons in low-density regions, solving part of the missing baryon problem, the sound of void boundaries. Sound waves don't propagate in the vacuum of space, but in the early universe, before atoms formed, conditions were very different. The cosmos was filled with a hot, dense plasma where sound waves could travel freely, creating oscillations in the distribution of matter and energy. These primordial sound waves left permanent imprints on cosmic structure, including the distribution and properties of cosmic voids. By measuring these imprints, called baryon-acoustic oscillations, astronomers use voids as precision rulers to measure the universe's expansion history. In the first 380,000 years after the Big Bang, matter and radiation were tightly coupled in a hot plasma. Pressure waves propagated through this plasma like sound waves in air, driven by the competition between radiation pressure pushing outward and gravity pulling inward. These oscillations created a characteristic scale the distant sound could travel before the universe cooled enough for atoms to form and the plasma to dissipate. This sound horizon was imprinted on the distribution of matter as a preferred separation scale between overdense regions. As the universe evolved and structure formed, this preferred scale persisted, creating subtle periodic features in how galaxies cluster. Galaxies are slightly more likely to be separated by distances corresponding to the sound horizon at recombination about 500 million light-years in today's universe than by other distances. This baryon acoustic oscillation signal appears as a bump in the galaxy correlation function, a statistical measure of how galaxy positions relate to each other. Cosmic voids also carry BAO signatures, but in opposite phases from galaxy clusters. While galaxies preferentially cluster at the BAO scale, voids are slightly more likely to be found at half that scale, about 250 million light-years, corresponding to acoustic troughs where matter was displaced away from underdense regions. This void BAO signal, though more challenging to measure than the galaxy BAO signal due to void's lower number density, provides independent constraints on cosmological parameters. The power of BAO measurements lies in their use as standard rulers. The physical scale is set by physics of the early universe and doesn't evolve with time. By measuring the apparent angular size of this scale at different redshifts, looking at voids and galaxies at various distances, astronomers can reconstruct the universe's expansion history. If expansion were constant, the BAO scale would appear proportionally smaller at greater distances. But deviations from this simple relationship reveal how expansion has accelerated or decelerated over cosmic time. Void BAO measurements offer several advantages over galaxy-based measurements. Voids probe underdense regions where systematic effects like galaxy bias, the tendency for galaxies to be more clustered than the underlying dark matter, are minimized. Voids also sample larger volumes than individual galaxies, potentially averaging over small-scale irregularities more efficiently. These properties make void BAO measurements a valuable complement to traditional galaxy BAO studies. Recent surveys have successfully detected BAO signals in void statistics. The BOSS, Baryon Oscillation Spectroscopic Survey, and eBOSS, Extended BOSS, collaborations measured void size distributions and void galaxy cross correlations, finding BAO features at the expected scales. Combined with galaxy BAO measurements, these void results tighten constraints on dark energy and spatial curvature, confirming that the universe is geometrically flat and that dark energy behaves consistently with a cosmological constant. The void BAO signal depends on how voids are defined. Different void-finding algorithms, watershed methods, spherical overdensity approaches, or dynamical criteria identify slightly different sets of voids with varying BAO properties. Researchers have devoted considerable effort to optimizing void definitions to maximize BAO signal strength while minimizing contamination from spurious voids or algorithm artifacts. The consensus is that large voids defined using underdensity criteria provide the cleanest BAO signal. Void sizes themselves carry cosmological information beyond BAO. The typical radius of large voids depends on the matter density, dark energy equation of state, and the power spectrum of primordial density fluctuations. By measuring how void size distributions evolve, with redshift comparing nearby voids to distant ones formed earlier in cosmic history, astronomers can constrain these fundamental parameters. Early results show that void sizes grow with time, as expected in expanding models, with growth rates consistent with LCDM predictions. One subtle effect concerns redshift space distortions, systematic shifts in apparent galaxy positions caused by their peculiar velocities. Galaxies don't just move with the cosmic expansion, they also have random motions and systematic flows toward overdense regions. These motions shift the galaxy's observed redshifts, making them appear at different distances than their true positions. This effect distorts void shapes, making them appear elongated along the line of sight in redshift surveys. By modeling these distortions, astronomers can extract information about velocity flows and gravitational growth rates that complement BAO measurements. Rogue objects in the void. Cosmic voids, though underdense, aren't completely devoid of objects. Besides the sparse dwarf galaxies discussed earlier, voids contain other surprising inhabitants: runaway galaxies, isolated star clusters, and even lone stars drifting through intergalactic space. These rogue objects, ejected from their parent systems through gravitational interactions or born in unusual circumstances, provide unique windows into violent cosmic processes and extreme environments. Hypervelocity stars represent one class of void objects. These are stars moving so fast, typically over 1,000 kilometers per second, well above galactic escape velocity, that they've been flung out of their home galaxies entirely. Most hypervelocity stars are thought to originate near galactic centers, where close encounters with supermassive black holes can accelerate stars to extreme velocities through a process called the Hills mechanism. In this scenario, a binary star system wanders too close to a black hole, which tears the pair apart, capturing one star while ejecting the other at tremendous speed. Dozens of hypervelocity stars have been identified, many travelling through the Milky Way's halo, but some projected to reach intergalactic space and enter cosmic voids. These stars carry chemical signatures of their galactic origins, metallicities, and abundance patterns, matching stars from galactic bulges or disks. By tracing their trajectories backward, astronomers can confirm they originated in the Milky Way or nearby galaxies millions of years ago. Their existence in void environments, far from any galaxy, demonstrates that violent ejection processes can scatter stellar material across truly cosmic distances. Intergalactic star clusters represent another void population. These are globular clusters, or dwarf galaxy remnants, that have been tidally stripped from larger galaxies and now orbit in intergalactic space. Observations have identified hundreds of such clusters in nearby galaxy groups and clusters, some residing in relatively low-density regions between galaxies. Whether any have reached the deepest voids remains uncertain, but dynamical models suggest that particularly violent galaxy interactions could launch clusters on trajectories, carrying them into void interiors over billions of years. Isolated planetary nebulae, dying stars shedding their outer layers, have been detected in intergalactic space, including possible void regions. These objects, though faint, can be identified through their characteristic emission lines. Their presence, far from any host galaxy, implies that their progenitor stars, likely hypervelocity stars ejected earlier, lived out their lives in isolation before dying. The nebulae drift through space as slowly expanding shells of gas, gradually fading as they disperse into the intergalactic medium. Some observations have suggested the possible existence of orphan black holes in voids, stellar mass, or even intermediate mass black holes, expelled from galaxies through recoil kicks, following asymmetric supernova explosions or black hole mergers. These objects would be essentially invisible, except for rare instances when they accrete gas or pass in front of background sources, creating transient lensing events. While none have been conclusively identified in voids specifically, their existence is theoretically plausible and might be revealed by future transient surveys. More speculative are proposed populations of dark galaxies systems consisting primarily of dark matter with little or no star formation. These would be dark matter halos that never accreted enough gas to form stars, or that lost their gas to feedback processes before significant star formation occurred. Some models predict that voids should contain substantial numbers of dark galaxies, particularly at smaller masses, where galaxy formation is inefficient. Detecting these objects requires indirect methods like gravitational lensing or searching for neutral hydrogen that might have accumulated in their halos despite the absence of stars. Recent radio surveys have identified several puzzling hydrogen clouds in apparent void regions with no associated optical galaxies. Some of these clouds might be dark galaxies, dark matter halos that retained cold gas but never formed many stars. Alternatively, they could be tidal debris stripped from galaxies during interactions, now floating freely through intergalactic space. Distinguishing these scenarios requires detailed follow-up observations, including deep optical and infrared imaging, to search for extremely faint stellar populations that might have been missed in shallower surveys. Another class of void objects includes intergalactic supernovae, stellar explosions occurring in isolation far from any host galaxy. While most supernovae trace to identifiable galaxies, a small fraction, perhaps 1 or 2%, appear hostless in deep images. Some of these likely belong to very faint dwarf galaxies below survey detection thresholds. But others might genuinely represent stars exploding in intergalactic voids. These could be hypervelocity stars that reach the endpoint of their evolution, or stars formed in unusual circumstances, like the tips of tidal tails during galaxy interactions. The distribution of rogue objects in voids provides constraints on galaxy interaction histories and ejection mechanisms. If hypervelocity star ejection is common, voids should contain a diffuse population of isolated stars and their remnants. Current estimates suggest that perhaps 0.01% of stars exist in truly intergalactic environments, translating to billions of stars scattered between galaxies in a typical galaxy cluster or group. How many have reached the deepest voids remains uncertain, but ongoing surveys discovering more hypervelocity stars will enable better estimates. The missing baryon mystery. For decades, astronomers faced an embarrassing problem. They couldn't find all the ordinary matter predicted to exist in the universe. The cosmic microwave background radiation, primordial element abundances, and other cosmological probes indicated that about 5% of the universe's total energy density consists of baryonic matter, protons and neutrons, the stuff of atoms and molecules. Yet when astronomers tallied up all the baryons they could detect in stars, galaxies, and gas clouds, only about half the predicted amount showed up. The rest, dubbed the missing baryons, remained hidden somewhere in cosmic structure. Theoretical models suggested where these missing baryons might reside, in a diffuse, warm-hot intergalactic medium, threading the cosmic web, including void regions. This gas, heated to temperatures between 100,000 and 10 million Kelvin by shock waves and gravitational heating as it falls into cosmic filaments, would be nearly invisible to conventional telescopes. Too hot to produce strong hydrogen emission, but too cool to emit bright X-rays. WIM occupied an observational blind spot that frustrated detection efforts for years. Several indirect methods eventually confirmed WIM's existence. One approach used quasar absorption spectroscopy to search for highly ionized metals like oxygen Vi and neon V8 ion species that exist only at WIM temperatures. When quasar light passes through WIM regions, these ions create absorption lines in the ultraviolet spectrum. Space telescopes, like the Hubble Space Telescope and the Far Ultraviolet Spectroscopic Explorer, detected these absorption systems along numerous quasar sightlines, confirming that warm hot gas exists throughout intergalactic space. The challenge was determining how much gas these absorption systems represented. Converting detected ions into total hydrogen mass requires assumptions about metallicity, ionization, state, and temperature, all highly uncertain. Different studies using different assumptions reached different conclusions about whether observed WIM could account for the missing baryons. Some estimates suggested that up to half the missing mass might reside in WHIM, while others found only 10 or 20%, leaving a substantial fraction still unaccounted for. Cosmic voids entered this story when researchers realized that voids might host a significant fraction of WIM and other hard-to-detect baryons. Though voids are underdense, they occupy such enormous volumes, roughly 80% of space, that even very low densities can add up to substantial total mass. If void gas exists at 10 or 20% of the cosmic average density, the integrated mass becomes significant on cosmic scales. Direct detection of void HIM proved even more challenging than detecting WIM in filaments, because the lower densities produce weaker absorption signals. However, stacking techniques combining spectra from many quasars, whose sightlines pass through voids, can amplify the weak signals. Recent studies using this approach have detected oxygen absorption consistent with WIM at void boundaries, and possibly extending into void interiors. The measured oxygen columns suggest substantial gas masses, though converting these to total hydrogen still involves significant uncertainties. X-ray observations provide an alternative WIM detection method. Hot plasma emits X-rays through thermal bremsstrahlung and line emission, with intensity depending on gas density squared. This means filaments, with their higher densities, dominate X-ray emission, even though voids contain more volume. Nevertheless, sensitive X-ray telescopes like Chandra and XMM Newton have detected faint, diffuse emission from low-density regions, including void peripheries. These detections confirm that million-degree gas exists in underdense regions, though whether it fills void interiors or primarily outlines their boundaries remains unclear. One innovative approach combines multiple observational techniques to constrain void baryon content. By measuring the Sunyaev-Zeldovich effect, distortions in the cosmic microwave background created when CMB photons scatter off hot electrons, and comparing it to other void observations, researchers can estimate the total electron content and thus the ionized gas mass. Early results from this technique suggest that voids do indeed contain diffuse ionized gas at levels consistent with harboring a substantial fraction of missing baryons. The temperature structure of this void gas matters for understanding its observability. If void gas is too hot above 10 million Kelvin, it would emit X-rays and be relatively easy to detect. If too cool, below 100,000 Kelvin, it would likely be neutral and detectable through hydrogen 21 centimeter emission. But if it occupies the WIM temperature range, it falls into the observational gap where detection is most difficult. Simulations suggest that void gas should indeed span this problematic temperature range, with typical temperatures around a few 100,000 Kelvin, precisely where detection is hardest. Recent advances in fast radio burst observations offer a promising new approach. Fast radio bursts passing through the universe accumulate dispersion, a frequency-dependent delay caused by free electrons along the propagation path. By measuring this dispersion and subtracting the known contributions from galaxy halos and the Milky Way, astronomers can infer the dispersion measure from the intergalactic medium, including voids. Comparing these measurements to matter distributions from galaxy surveys reveals electron densities in different environments. Preliminary results indicate that low-density regions, possibly including voids, contain more ionized gas than expected from simple models, supporting the idea that voids harbor missing baryons. Solving the missing baryon problem requires understanding where baryons reside at different cosmic epochs. In the early universe, most baryons existed as diffuse hydrogen gas or in early galaxies. Over time, some collapsed into galaxies and stars, while others were heated and expelled into the intergalactic medium by feedback processes. The current baryon census must account for all these components: stars and cold gas in galaxies, hot gas in galaxy halos, warm-hot intergalactic medium in filaments, and potentially substantial reservoirs in cosmic voids, void shapes, and the cosmic web. Cosmic voids aren't perfect spheres floating randomly through space. They have complex, irregular shapes, elongated, squashed, or triaxial, reflecting the gravitational environment in which they formed and evolved. These shapes encode information about cosmic structure formation, the nature of dark energy, and the large-scale distribution of matter throughout the universe. By carefully measuring void shapes and their evolution over cosmic time, astronomers can test fundamental assumptions about cosmology and gravitational physics. The shape of a void depends on the distribution of matter in its surroundings. If a void forms in a region where matter is uniformly distributed in all directions, it will naturally evolve toward a spherical shape, the configuration that minimizes surface area for a given volume. But the cosmic web isn't uniform. Matter concentrates along filaments and nodes, creating anisotropic gravitational fields that stretch and compress voids into elongated or flattened forms. Measurements of void shapes from galaxy surveys reveal that most voids are indeed non-spherical, with axis ratios typically ranging from 5:1 to 3:1, moderately to significantly elongated. The degree of elongation correlates with void size. Smaller voids tend to be more spherical, while larger voids show greater ellipticity. This size-shape relationship likely reflects the hierarchical nature of structure formation. Small voids form in more uniform local environments and haven't existed long enough for large-scale tidal fields to significantly distort them. Large voids, by contrast, span regions influenced by multiple massive structures whose combined gravitational fields shape them into asymmetric configurations. The orientation of void shapes also carries information. If voids aligned randomly, their major axes would point in arbitrary directions with no preferred orientation. But observations show that large voids tend to align with the cosmic web's filamentary structure. Void major axes preferentially point along the directions connecting neighboring galaxy clusters or parallel to nearby filaments. This alignment indicates that voids' shapes are actively molded by the gravitational fields of their surroundings. They're stretched in the directions where expansion is easiest and compressed, where massive structures confine them. These shape alignments provide tests of gravitational theory. In Einstein's general relativity, the relationship between matter distribution and tidal gravitational fields is precisely specified. Alternative theories of gravity modifications proposed to explain cosmic acceleration without dark energy predict different tidal field strengths for the same matter distribution. By measuring void shapes and comparing them to the matter distributions that produce them, astronomers can test whether gravity behaves as Einstein predicted on scales of hundreds of millions of light-years. Void shapes also affect cosmological measurements that use voids as probes. The Alcock-Paczynski test, for instance, uses the apparent shapes of cosmic structures to measure the universe's expansion history. If a structure is intrinsically spherical, its apparent ellipticity on the sky reveals the ratio of angular to radial distances, which depends on cosmological parameters. For voids, uncertainties about their intrinsic shapes complicate this test. If voids aren't truly spherical, their apparent shapes mix intrinsic elongation with cosmological effects. Careful statistical analysis can separate these effects, but it requires large void samples and precise shape measurements. The evolution of void shapes over cosmic time provides additional constraints on dark energy. In a matter-dominated universe, gravitational forces would gradually make voids more spherical as they evolve. Tidal fields weaken as the universe expands, allowing voids to relax toward equilibrium shapes. But dark energy's repulsive gravity opposes this trend, potentially preserving or even enhancing void elongations. By comparing void shapes at different redshifts, nearby voids versus distant ones, seen as they were billions of years ago, astronomers can detect dark energy's influence on structure evolution. Recent simulations have explored how different void shapes affect their internal dynamics. Elongated voids show more complex velocity fields than spherical ones, with matter flowing not just radially outward from their centers, but also along their major axes toward the poles. These flows reflect the anisotropic gravitational potentials of elongated voids, and can be detected through careful analysis of galaxy velocities in and around voids. Measuring these velocity patterns provides additional tests of gravitational physics and void formation models. Some researchers have proposed using void shapes as cosmological standard rulers, analogous to how baryon acoustic oscillations use a standard length scale. If voids at a given size have characteristic shapes determined by universal physical processes, then measuring how these shapes appear at different distances could constrain cosmological parameters. This approach is still in early development, requiring better understanding of what determines void shapes and whether they're sufficiently universal to serve as standard objects. The void shape distribution itself, how common different elongations and asymmetries are, constrains models of structure formation. Simulations predict specific shape distributions depending on cosmological parameters like matter density, dark energy properties, and the primordial power spectrum. By measuring shape distributions from observations and comparing them to simulation predictions, astronomers can test cosmological models. Current measurements generally agree with standard LCDM predictions, though uncertainties remain large enough to allow for some modifications. Gravitational lensing by negative mass. Gravitational lensing, the bending of light by gravity, has become one of astronomy's most powerful tools, revealing dark matter distributions, measuring cosmic distances, and even detecting distant exoplanets. But most lensing studies focus on massive objects, like galaxy clusters, that focus light, creating magnified and distorted images of background sources. Cosmic voids, with their deficit of mass, produce the opposite effect. They defocus light, creating a subtle demagnification signal that's far more challenging to detect, but equally valuable for understanding cosmic structure. The basic physics of void lensing follows from general relativity. Mass curves space-time, and light follows those curves. Dense objects like clusters create convergent gravitational fields that focus light rays toward us, making background galaxies appear brighter and larger. Voids, being underdense, create divergent fields that spread light rays apart, making background sources dimmer and smaller. This demagnification is accompanied by a characteristic distortion pattern, tangential stretching around the void's edges, that can be detected through statistical analysis of background galaxy shapes. Measuring void lensing presents significant technical challenges. The signal is weak. Typical demagnifications are only a few percent and must be extracted from noisy data containing thousands of galaxies with intrinsic shape variations that dwarf the lensing signal. Early attempts to detect void lensing found only marginal evidence, with results consistent with predictions but with large uncertainties. Success required both larger surveys, providing better statistics, and refined analysis techniques that could distinguish tiny lensing distortions from noise and systematic errors. Recent studies using data from surveys like the Kilo Degree Survey, KIDS, and the Dark Energy Survey, DES, have achieved robust detections of weak lensing by cosmic voids. By carefully stacking signals from hundreds or thousands of voids, researchers amplified the weak individual signals enough to reach statistical significance. The detected lensing profiles how the signal varies with distance from void centers match theoretical predictions reasonably well, confirming that voids do indeed demagnify background sources as expected. These measurements provide several valuable scientific returns. First, They allow direct measurement of the total mass, including dark matter, in void regions, free from assumptions about how galaxies trace matter. This complements galaxy-based void definitions and helps calibrate the relationship between galaxy density and total matter density in underdense regions. Results show that the most empty voids defined by galaxy surveys typically contain 20 to 40% of the cosmic average matter density, with the exact value depending on void size and definition. Second, void lensing tests gravitational physics in regimes unexplored by cluster lensing. Modified gravity theories often predict departures from general relativity that become apparent in low-density regions where gravitational potentials are weak. By measuring how efficiently it voids lens background light and comparing this to predictions from different gravity theories, astronomers can constrain modifications to Einstein's equations. So far, void lensing measurements favor standard general relativity, though current uncertainties still permit modest deviations. Third, the combination of void lensing with other void observables enables new cosmological tests. For instance, combining lensing measurements, which probe total matter, with galaxy counts, which trace visible matter, constrains galaxy bias in voids, how strongly galaxies cluster relative to dark matter. This bias differs in voids compared to average or overdense regions, and understanding these differences improves our ability to use galaxies as matter tracers across all environments. One surprising finding from void lensing studies concerns void profiles, how matter density varies with distance from void centers. Simple models assume monotonic profiles with density increasing steadily from void centers toward their edges. But lensing measurements hint at more complex structures, with some voids showing plateau-like regions where density remains roughly constant over large radial ranges, and others exhibiting excess mass near their centers relative to simple profiles. These complexities might reflect hierarchical structure formation, with smaller voids and filaments nested within larger voids, or dynamical effects from void expansion and evolution. The shape of void lensing profiles at large radii, well outside the void boundary as defined by galaxy surveys, probes the transition from void interiors to the surrounding cosmic web. Measurements show that demagnification signals persist well beyond void edges, gradually transitioning to magnification as the matter density rises above average in void walls and filaments. The width of this transition zone constrains how sharply defined void boundaries are and how abruptly density changes at the interface between voids and filaments. Future improvements in void lensing measurements will come from several directions. Larger surveys like Euclid and the Vera Rubin Observatory's Legacy Survey of Space and Time will provide both more voids and more background galaxies for shape measurements, dramatically improving statistical precision. Better shape measurement algorithms reduce systematic errors from PSF, point spread function, effects, and other instrumental artifacts that can mimic or obscure real lensing signals. And more sophisticated theoretical modeling accounts for complexities like void triaxiality and substructure that affect lensing profiles in ways not captured by simple spherical models. The coldest spots in the universe. Temperature might seem like a meaningless concept in the near vacuum of cosmic voids, but the tenuous matter that exists there, both gas and the quantum vacuum itself, has measurable thermal properties that reveal fundamental physics. Some void regions may contain the coldest naturally occurring matter in the entire universe, with temperatures approaching absolute zero far more closely than anything achievable in laboratories on Earth. Understanding these ultra-cold environments provides insights into thermodynamics on cosmic scales and tests predictions about matter's behavior in extreme conditions. The temperature of gas in voids depends on a balance between heating and cooling processes. Heating comes primarily from photoionization by the cosmic ultraviolet background radiation from distant quasars and star-forming galaxies that permeates intergalactic space. When UV photons ionize hydrogen atoms, they convert electron-binding energy into kinetic energy, heating the gas. This process maintains temperatures around 10,000 to 20,000 Kelvin in typical intergalactic regions. But in the deepest voids, far from any galaxies, the UV background intensity drops. Fewer photons reach these remote locations, both because sources are scarce in voids and because intervening gas absorbs UV radiation during its journey. With reduced photoionization heating, void gas can cool below typical intergalactic temperatures. Cooling mechanisms include adiabatic expansion as the universe and voids themselves expand, Compton scattering against the cosmic microwave background, which cools the gas while heating the CMB photons, and radiative cooling through atomic transitions. Theoretical models predict that gas in the emptiest void centers might cool to temperatures as low as 3,000 to 5,000 Kelvin, approaching cosmic microwave background temperature, which is 2.7 Kelvin. At these temperatures, hydrogen remains largely ionized due to the residual UV background. But cooling efficiency increases and heating decreases, pushing temperatures ever lower. Some models even suggest that isolated pockets of neutral hydrogen might survive in void centers if the local UV intensity falls low enough, creating cold, neutral clouds in otherwise ionized surroundings. Detecting this ultra-cold gas presents extraordinary challenges. Neutral hydrogen emits the 21 centimeter line, but only if the gas is cold enough that the spin temperature which governs the line's strength remains low. Proposals exist to use next-generation radio telescopes like the Square Kilometre Array to search for faint 21 centimeter emission or absorption from void centers, potentially revealing these cold hydrogen clouds if they exist. Success would provide direct measurement of the coldest, naturally occurring gas in the universe. Another temperature frontier concerns the quantum vacuum itself. Quantum field theory predicts that even completely empty space contains zero-point energy quantum fluctuations that create and annihilate virtual particles on timescales too brief to violate energy conservation. This vacuum energy contributes to the cosmological constant and dark energy, but its effective temperature is less clear. In highly underdense regions, like void centers, where matter, density, and interactions approach zero, the quantum vacuum's properties might manifest in subtle but potentially observable ways. Some theoretical physicists have speculated about exotic vacuum states that might exist in voids regions where quantum fields settle into energy minima different from the standard vacuum state. These false vacuum regions, if they exist, could have slightly different physical constants or particle properties than normal space. Though highly speculative and not predicted by standard physics, such regions would be most likely to form in voids where particle densities are lowest and external influence is minimal. No evidence for such exotic vacuum states has been found, but searches continue. The CMB itself provides a temperature floor for the universe. CMB photons bathe all of space in a 2.7 Kelvin thermal bath, and any colder gas would be heated by absorbing these photons. This sets an absolute minimum temperature for matter in voids nothing can cool below the CMB temperature through thermal processes. However, rare adiabatic expansion events, like gas flowing into an expanding void, might briefly cool matter below CMB temperature in local regions before rethermalization occurs. These transient cold spots, if they exist, would be vanishingly difficult to detect. Observations searching for temperature variations in void gas have found intriguing hints. Quasar absorption line studies show that the typical temperature-density relation hotter gas at higher densities extends down to the lowest densities, but with increasing scatter. Some low-density absorption systems show unexpectedly narrow lines, suggesting temperatures below 10,000 Kelvin, though interpretation is complicated by uncertainties about turbulence, peculiar velocities, and other broadening mechanisms besides temperature. Laboratory experiments on Earth routinely achieve temperatures far below those found anywhere in nature, using sophisticated cooling techniques like laser cooling and evaporative cooling. The coldest laboratory temperatures reach billionths of a Kelvin, creating exotic quantum states like Bose-Einstein condensates. But these conditions require active intervention, removing energy through controlled processes. In space, absent such intervention, voids might represent nature's closest approach to absolute zero through purely thermodynamic means. The quantum, vacuum, and void physics. The notion of empty space has troubled physicists since the advent of quantum mechanics. In classical physics, a vacuum meant absolute nothingness, no particles, no fields, no energy. But quantum theory reveals that even the emptiest space seethes with activity. Virtual particles constantly pop into and out of existence, borrowing energy from the vacuum for timescales so brief that Heisenberg's uncertainty principle permits the loan. This quantum foam, as it's sometimes called, imbues the vacuum with an intrinsic energy density that might manifest most clearly in cosmic voids, the closest approximations to true emptiness that nature provides. The energy of the quantum vacuum connects directly to cosmology's greatest mystery, dark energy. The cosmological constant in Einstein's equations can be interpreted as vacuum energy, a baseline energy density pervading all of space. Theoretical calculations attempting to predict this vacuum energy from quantum field theory famously produce results 120 orders of magnitude larger than observed. A discrepancy so severe it's been called the worst prediction in physics. Yet the vacuum energy must exist at some level, driving the universe's accelerated expansion. Cosmic voids, with their minimal matter, content, and maximal volume, become natural places to study vacuum properties. Several theoretical frameworks predict that vacuum energy might vary slightly across space rather than being perfectly uniform. In these models, the vacuum settles into different energy states in different regions, with phase transitions between states occurring at boundaries. Cosmic voids, having formed through gravitational evolution that evacuated matter, might also have developed distinct vacuum properties during their formation. If vacuum energy were slightly lower in voids than in filaments, this would enhance void expansion beyond what matter distribution alone predicts. Conversely, higher vacuum energy in voids would resist expansion, potentially explaining why some voids grow more slowly than models predict. Testing these ideas requires exquisite precision. Any vacuum energy variations would produce tiny differences in how cosmic expansion proceeds in voids versus average regions. The Alcock-Paczynski test, comparing radial to tangential distances for voids at different redshifts, might detect such effects if vacuum energy varies with density. Similarly, measurements of void expansion rates using galaxy velocities could reveal departures from predictions based on matter content alone, potentially signaling vacuum energy that responds to local density. The Casimir effect, an experimentally verified phenomenon where quantum vacuum fluctuations create measurable forces between conducting plates, offers another connection between quantum vacuum physics and cosmic voids. In laboratory experiments, two parallel metal plates placed in vacuum experience an attractive force because vacuum fluctuations between the plates are restricted to wavelengths that fit in the gap, while outside the plates all wavelengths contribute. This asymmetry creates a net force pushing the plates together. Some theorists have speculated about analogous cosmic Casimir effects, where the geometry of cosmic structure, particularly the spherical or elongated boundaries of voids, might modify vacuum fluctuations in ways that affect structure evolution. Detecting cosmic Casimir effects would require identifying subtle correlations between void shapes, sizes, and expansion rates that couldn't be explained by gravity and matter distribution alone. No such effects have been confirmed, and many physicists doubt they'd be significant on cosmic scales where quantum effects typically wash out. But the theoretical possibility remains, and increasingly precise void measurements might eventually constrain or rule out cosmic Casimir physics. Particle physics offers additional connections to void physics through the concept of true and false vacua. In some quantum field theories, the vacuum we observe might not represent the lowest possible energy state. It could be a metastable false vacuum that will eventually decay to a true vacuum with lower energy. Such a phase transition would be catastrophic, releasing enormous energy and potentially changing the laws of physics throughout the affected region. If this sounds like science fiction, it's worth noting that similar phase transitions occurred in the early universe, including the electroweak transition that gave particles their masses. Cosmic voids have been proposed as possible sites where vacuum instabilities might nucleate. Their low matter density means fewer particles to stabilize the current vacuum state, potentially allowing quantum tunneling to alternative vacua. If a true vacuum bubble nucleated in a void center, it would expand at light speed, converting false vacuum to true vacuum and releasing energy that could be detectable as a sudden, expanding shell of radiation. Searches for such events in deep sky surveys have found nothing, suggesting either that our vacuum is stable, that tunneling rates are far lower than some theories predict, or that we've simply been fortunate enough not to witness such a transition. The zero-point energy of quantum fields, the lowest energy state they can occupy, also contributes to vacuum energy and might vary in voids. Each quantum field has a characteristic zero-point energy determined by its properties, and if fields behave differently in extremely low-density environments, their zero-point contributions might shift. Theories exploring this possibility suggest that fields coupled to matter density, like the Higgs field, might indeed show different vacuum expectation values in voids versus filaments. These variations would be minute, but might accumulate over cosmic distances to produce observable effects. One intriguing proposal suggests using the cosmic microwave background to search for quantum vacuum signatures in voids. If vacuum properties differ between voids and filaments, CMB photons might experience slightly different propagation speeds or scattering cross-sections when passing through different regions. This would create temperature correlations between CMB maps and void catalogues, beyond what the integrated Sachs-Wolf effect predicts. Several groups have searched for such anomalous correlations, but found none exceeding expected statistical noise, suggesting vacuum properties are uniform to high precision or that proposed effects were too optimistic. Void galaxies and cosmic isolation. Among the most peculiar inhabitants of cosmic voids are the galaxies that somehow formed and survived in these underdense regions. These void galaxies represent natural experiments in isolation systems that have evolved for billions of years with minimal external influence, free from the mergers, tidal interactions, and environmental processing that shape galaxies in denser regions. By studying how void galaxies differ from their cluster-dwelling cousins, astronomers can isolate the effects of the environment from intrinsic physical processes, answering fundamental questions about what drives galaxy evolution. The most striking characteristic of void galaxies is their youth. Spectroscopic observations reveal that void galaxies, on average, have younger stellar populations than galaxies of similar mass in filaments or clusters. Their light is dominated by blue, hot, massive stars characteristic of ongoing star formation, while comparable mass galaxies in dense environments often show red spectra, indicating older, cooler stellar populations with little active star formation. This dichotomy reflects fundamentally different evolutionary paths. Void galaxies retain their gas reservoirs and continue forming stars at rates similar to those in the early universe, while cluster galaxies have been stripped of gas or had their star formation quenched by environmental processes. Measurements of void galaxy rotation curves how orbital velocity varies, with radius reveal extended gaseous disks stretching far beyond the stellar component. In dense environments, ram pressure from hot intracluster gas and tidal forces from neighbouring galaxies truncate gaseous disks, limiting their extent. Void galaxies, free from such harassment, maintain their gas out to large radii, where it provides fuel for continued star formation. Some void spirals show gas disks extending to twice the radius of their stellar disks, configurations rarely seen in cluster environments. The metallicity of void galaxies, their content of elements heavier than helium, provides another evolutionary tracer. Stars produce heavy elements through nuclear fusion and distribute them through supernovae and stellar winds. Over cosmic time, successive generations of stars enrich galaxies with metals, gradually increasing their metallicity. Void galaxies typically show lower metallicities than similar mass galaxies in denser regions, indicating less cumulative star formation and chemical evolution. This deficit suggests void galaxies formed later or evolved more slowly, consistent with delayed structure formation in underdense regions. Interestingly, the metallicity gradients within void galaxies in how metal content varies, with radius often differ from those in field galaxies. Many void spirals show flatter gradients, with central and outer regions having more similar metallicities than typical spirals. This flattening might result from less centralized star formation, with gas flows driven by stellar feedback redistributing metals more uniformly throughout the disk. Alternatively, accretion of metal-poor gas from the intergalactic medium might dilute central metallicities while enriching outer regions, creating flatter gradients. The morphologies of void galaxies present puzzles. Spiral galaxies dominate in voids, with elliptical and lenticular galaxies being rare, the opposite of what's observed in dense clusters where ellipticals dominate. This morphology-density relation has been recognized for decades, but void studies sharpen its implications. The scarcity of ellipticals in voids suggests these morphologies arise primarily through mergers and interactions common in dense environments, while spirals represent the default evolutionary outcome for isolated systems. Some researchers propose that all modern ellipticals formed through major mergers of spirals. And since voids lack the galaxy density needed for frequent mergers, ellipticals simply don't form there. However, some void ellipticals do exist, creating a puzzle. How did these systems form in isolation without the mergers thought necessary to create elliptical morphologies? Detailed studies of void ellipticals suggest several possibilities. Some may be fossil groups, the last survivors of small galaxy groups that formed in slightly overdense regions within voids, where limited mergers occurred before the systems were too dispersed by void expansion. Others might be compact, early-type galaxies born directly from gas collapse without ever forming a spiral disk, though such formation pathways remain uncertain. The dynamics of void galaxies also differ from their environment-rich counterparts. Measurements of velocity, dispersions, the random motions of stars within galaxies show that void spirals often have lower dispersions than comparable field spirals. This kinematic coldness suggests void galaxies have experienced fewer violent events that would heat stellar populations. Their stars orbit the galactic center on more circular, ordered paths, reflecting tranquil formation and evolution. This dynamical difference extends to dark matter halos. Simulations predict void galaxy halos should be less concentrated and more circular than halos in dense regions, consequences of their quieter assembly histories. Some void galaxies show unusual asymmetries and disturbances despite their isolation. Tidal tails, warped disks, and other features typically associated with interactions appear in a fraction of void systems. These disturbances might be fossil evidence of ancient encounters that occurred before the galaxies became truly isolated, when the universe was younger and denser. Alternatively, some might result from dark matter subhalo encounters, interactions with invisible dark matter clumps that don't contain galaxies but exert gravitational forces. Identifying such dark matter-induced disturbances would provide rare direct evidence of dark matter's presence beyond its gravitational effects on large scales. The smallest void galaxies, dwarf irregulars, and transitional dwarfs represent the faintest systems forming in isolation. These galaxies, with stellar masses 1,000 times smaller than the Milky Way, barely qualify as galaxies at all, containing only millions of stars. Yet they follow similar patterns to larger void galaxies: active star formation, blue colors, low metallicities, and extended gas disks. Some extremely faint void dwarfs might represent the smallest halos capable of forming stars in low-density environments, providing crucial data for theories of galaxy formation thresholds and the role of feedback in regulating star formation. Void galaxy surveys have uncovered several fossil systems galaxies with signatures of past events now long finished. One example includes galaxies with old stellar populations in their centers, surrounded by young stars in their outskirts, suggesting episodes of star formation that progressed outward over time. Another involves galaxies with disturbed morphologies but no visible companions, indicating past interactions where the companion either merged completely or escaped. These fossils preserve evidence of void galaxies' full evolutionary histories, revealing that even isolation doesn't guarantee complete tranquility across billions of years. The sound horizon in void statistics. In the universe's first 380,000 years, before atoms formed and photons decoupled from matter, sound waves propagated through the hot plasma filling space. These pressure waves, driven by the competition between radiation pressure pushing outward and gravity pulling inward, created periodic compressions and rarefactions in the matter distribution. When atoms finally formed and the plasma became neutral gas, these sound waves froze into the matter distribution as a characteristic scale to the sound horizon, roughly 150 megaparsecs in co-moving units. This scale appears throughout the universe as a subtle excess in the probability of finding galaxies separated by that distance, known as the baryon acoustic oscillation feature. Cosmic voids also carry this baryon acoustic imprint, but in opposite phase from galaxy clustering. Where sound waves compressed matter, galaxies preferentially formed, creating the BAO peak in galaxy clustering. But the troughs between acoustic compressions regions, depleted of matter, evolved into cosmic voids. This means voids should show a characteristic size distribution with a subtle peak corresponding to half the sound horizon, about 75 megaparsecs, where matter was most strongly depleted before structure formation began. Detecting this void BAO signal requires carefully measuring the size distribution of thousands of voids across large cosmic volumes. The signal is subtle, a few percent enhancement in the number of voids at the BAO scale compared to adjacent scales, and can be obscured by selection effects, void definition systematics, and cosmic variance. Early searches produced tentative detections with large error bars, but recent analyses using larger surveys have achieved statistically significant measurements, confirming that void size distributions do indeed show the predicted BAO feature. The utility of void BAO measurements lies in their complementarity to galaxy BAO studies. Voids probe underdense regions where systematic effects that complicate galaxy clustering measurements, like galaxy bias, redshift space distortions, and nonlinear gravitational evolution, operate differently. By combining void and galaxy BAO measurements, astronomers can break degeneracies between cosmological parameters and systematic effects, achieving tighter constraints than either probe provides alone. One particularly powerful application uses the Alcock-Paczynski test applied to void shapes. If voids are statistically spherical in real space, their apparent shapes in redshift surveys encode the ratio of transverse to line-of-sight distances, which depends on cosmological parameters including dark energy properties. The BAO scale provides a standard ruler for this test. If void sizes at the BAO scale differ in transverse versus radial directions, it indicates distortions from incorrect cosmological assumptions in converting redshifts to distances. Implementing this test requires careful treatment of several complications. Redshift space distortions, systematic shifts in apparent positions caused by galaxy peculiar velocities, affect void shapes, elongating them along the line of sight. This effect must be modelled and removed to access the geometric signal. Additionally, voids aren't perfectly spherical, even in real space, having intrinsic ellipticities from tidal gravitational fields. Statistical approaches, averaging over many voids, help separate intrinsic from cosmological shape distortions. The evolution of the void BAO signal with cosmic time provides additional leverage. By measuring void size distributions at different redshifts, nearby voids versus distant ones seen billions of years ago, astronomers can trace how the BAO scale appears to change with distance. This apparent evolution reveals the universe's expansion history, with accelerating expansion causing the BAO scale to appear different at different epochs in specific ways that constrain dark energy's evolution. Recent theoretical work has explored higher-order statistics beyond simple void-size distributions. The three-point correlation function, measuring how void positions correlate in triplets rather than pairs, contains additional BAO information not captured by size distributions alone. Similarly, analyzing voids' shapes and orientations relative to each other might reveal BAO signatures in configurational statistics. These advanced approaches remain in early stages, but promise to extract more cosmological information from void catalogues. One challenge in void BAO studies involves the precise definition of what constitutes a void. Different void-finding algorithms identify slightly different structures as voids, and the BAO signal strength depends on this definition. Watershed algorithms that identify voids as basins in the density field produce different catalogues than spherical underdensity methods that grow spheres until reaching a density threshold. Researchers have worked to optimize void definitions for BAO measurements, finding that large voids defined by significant underdensity thresholds produce the clearest BAO signals. The relationship between void BAO and galaxy BAO measurements reveals interesting physics. In principle, since voids and galaxies trace the same underlying matter distribution, just in opposite density regimes, they should yield consistent cosmological constraints. Discrepancies might indicate problems with our understanding of galaxy bias, how galaxy clustering relates to matter clustering, or reveal non-linear gravitational effects that differ between overdense and underdense regions. To date, void and galaxy BAO measurements agree reasonably well, supporting the validity of both approaches. Future void BAO studies will benefit from next-generation spectroscopic surveys like DESI, Dark Energy, Spectroscopic Instrument, and Euclid, which will map tens of millions of galaxy redshifts over vast volumes. These surveys will catalogue hundreds of thousands of voids, reducing statistical uncertainties to the point where void BAO measurements rival or exceed the precision of galaxy-based approaches. Combined analyses using both probes will provide some of the tightest constraints on dark energy and modifications to general relativity achievable with foreseeable surveys. Cosmic strings and topological defects in voids. Some of the most exotic theoretical predictions in cosmology involve topological defects, structures that might have formed during phase transitions in the early universe when fundamental forces separated and symmetries broke. Among these hypothetical objects are cosmic strings, one-dimensional defects analogous to cracks in ice, potentially stretching across cosmic distances with enormous linear mass densities. If cosmic strings exist, cosmic voids might be the best places to find them, as their signatures would be least contaminated by the complex structure in dense regions. Cosmic strings are predicted by certain grand unified theories and string theory scenarios describing physics at energy scales far beyond what particle accelerators can reach. During phase transitions in the universe's first fraction of a second, as the cosmos cooled from unimaginably hot conditions, symmetries in the laws of physics could have broken in different ways in different regions. At boundaries between regions where symmetry breaking took different orientations, energy would become trapped in linear configurations, cosmic strings unable to relax to the new vacuum state. These strings, if they exist, would have extraordinary properties. Despite being thinner than atomic nuclei in cross-section, they'd have masses of roughly 10-22 kilograms per meter. A single meter of cosmic string would outweigh Mount Everest. Strings could extend across substantial fractions of the observable universe, or form closed loops oscillating under their own tension. Moving strings would create gravitational shock waves, and their tremendous energy density would gravitationally lens background light in distinctive patterns. The connection to cosmic voids arises because string networks evolve differently in overdense versus underdense regions. In dense areas, string segments interact frequently, reconnecting when they cross and breaking into smaller loops. These interactions dissipate the network's energy through gravitational radiation, gradually eroding the strings. But in voids, where matter density is low and expansion rapid, string segments might survive longer, experiencing fewer interactions. Long, relatively straight string segments could persist in void interiors, while dense regions contain only short, rapidly decaying loops. Searching for cosmic strings requires looking for their gravitational signatures. A long, straight cosmic string would create a distinctive lensing pattern, a double image of background galaxies aligned along the string's length, with a characteristic deficit of images directly behind the string. Unlike normal gravitational lenses from massive objects that create complete Einstein rings or multiple images, string lensing produces pairs of images without the circular symmetry of standard lenses. This unique signature makes string lensing events theoretically identifiable, though none have been confirmed despite dedicated searches. Cosmic strings would also create discontinuities in the cosmic microwave background. Strings moving through the CMB emitting surface when that radiation was released would create step-like temperature jumps extending across the sky along the string's path. These Gott-Kaiser-Stebbins patterns, named after the theorists who predicted them, would appear as straight or gently curved lines in CMB maps. Searches through Planck satellite data have found no convincing candidates, placing upper limits on cosmic string tensions, mass per unit length, that rule out the strongest strings predicted by some theories, but still allow strings with lower tensions. Within cosmic voids, strings might create observable structure. A string passing through a void would gravitationally attract nearby gas and dark matter, potentially creating a filamentary overdensity aligned with the string. Such string-generated filaments might be detectable as linear galaxy alignments or gas concentration in otherwise empty voids. However, distinguishing string-generated filaments from ordinary filaments formed by gravitational instability requires careful analysis, and no definitive examples have been identified. Some cosmological models propose that cosmic strings could have seeded structure formation, with their gravitational fields creating initial density perturbations that grew into galaxies and clusters. In these scenarios, the pattern of cosmic structure, including the distribution of voids, would reflect the initial string network's geometry. Void shapes and orientations might preserve signatures of string orientations billions of years ago, before the strings decayed or dissipated. Statistical analyses searching for such patterns in void catalogues have found nothing inconsistent with standard structure formation from quantum fluctuations, constraining the role strings could have played. Other topological defects besides strings might exist in voids. Domain walls, two-dimensional surfaces separating regions where scalar fields took different values, could have formed during phase transitions. Unlike strings, domain walls have such high energy density that their existence would drastically alter cosmological evolution unless they quickly disappeared or never formed in significant numbers. Monopoles' point-like defects are also predicted by some theories, but face similar overproduction problems. The apparent absence of these defects, despite theoretical predictions, motivates models of cosmological inflation, which dilutes any primordial defects to undetectable densities. One intriguing possibility involves hybrid defects textures where multiple fields wind around each other in complex configurations. These structures could be more stable in low-density environments like voids, persisting longer than simple defects that quickly unwind. Some textures might even be effectively invisible, except through subtle gravitational effects or interactions with specific particle species, making them extraordinarily difficult to detect, but potentially significant for dark matter or dark energy. The absence of detected cosmic strings provides valuable information. Current observational limits constrain string tensions to levels where their contribution to structure formation and gravitational wave backgrounds must be subdominant. These constraints help rule out certain grand unified theories and parameter ranges in string theory, demonstrating how cosmological observations of voids and large-scale structure connect to fundamental physics at the smallest scales. Void mergers and the evolution of emptiness. Cosmic voids don't remain static, isolated structures throughout their existence. Like galaxies that merge to form larger systems, voids can collide and coalesce, creating progressively larger empty regions as the universe ages. Understanding void mergers is crucial for interpreting void populations and using voids as cosmological probes, as merger histories affect void properties in ways that must be accounted for in theoretical models. The process of void merging begins when two expanding voids' boundaries approach each other. Between them lies a wall of matter, the accumulated material drained from both voids during their formation and growth. As the voids continue expanding, this intervening wall thins and weakens. Eventually, if conditions are right, the wall can be breached, allowing the two voids to merge into a single larger void. The remnant inherits properties from both parents, but develops new characteristics determined by the merger dynamics. Identifying merging voids in observational data requires careful analysis. The clearest signature is an asymmetric void with a density saddle point rather than a single minimum, a shape suggesting two density minima not yet fully merged. Such peanut-shaped voids appear in surveys, their double-lobed morphologies indicating recent or ongoing mergers. Over time, as the merged system expands and internal flows redistribute matter, the morphology should relax toward a more spherical configuration, erasing evidence of the merger's occurrence. Simulations of cosmic structure formation show that void mergers are common throughout cosmic history. Small voids that form early often merge with neighbors, building larger voids through hierarchical assembly, analogous to how galaxy clusters form from smaller groups. This hierarchical growth contributes to the evolution of the void size distribution. Early epochs have many small voids and few large ones, while later times show fewer total voids, but a larger proportion of big ones. Measuring how void size distributions change with redshift provides tests of this evolutionary scenario. The dynamics of void mergers differ fundamentally from galaxy cluster mergers, despite superficial similarities. Cluster mergers are driven by gravitational attraction over dense regions pull toward each other, accelerating as they approach and colliding violently. Void mergers, by contrast, result from expansion under dense regions push outward, their boundaries meeting where the push balances between them. The collision isn't energetic, but rather a gradual dissolution of the boundary, as both voids' expansion dominates the intervening wall's gravity. Matter distribution after void mergers shows characteristic patterns. Simulations reveal that recently merged voids often retain substructure mini-filaments and residual walls internally marking the former boundary between parent voids. These features gradually dissolve as expansion continues and galaxy orbits mix, but they can persist for billions of years, creating complex internal structure in large voids. Detecting such substructure observationally would provide direct evidence of merger histories and constrained timescales for how quickly voids erase their merger signatures. The walls between merging voids are dynamically interesting regions. As two expanding voids squeeze an intervening wall from both sides, the wall experiences compression that can trigger enhanced star formation. Galaxies in these walls might show elevated star formation rates compared to typical void wall galaxies, creating a merger-induced starburst signature. Some researchers have searched for such enhanced activity in saddle region galaxies between close void pairs, with tentative evidence for elevated star formation, though confirmation requires larger samples. Void merger rates how frequently mergers occur as a function of cosmic time encode cosmological information. The merger rate depends on void expansion speeds, which in turn depend on the universe's matter content and dark energy properties. In a dark, energy-dominated universe, void expansion accelerates over time, potentially increasing merger rates at late epochs. Measuring these rates from observations and comparing them to theoretical predictions could provide additional constraints on dark energy evolution. One complication in studying void mergers involves selection effects. Void-finding algorithms typically search for the largest, most prominent voids, potentially missing or fragmenting voids caught mid-merger. A partially merged system might be identified as two separate voids rather than one merging system, or conversely, treated as a single irregular void without recognizing its composite nature. Developing merger-aware void-finding algorithms that can identify and characterize merging systems represents an ongoing research challenge. The largest voids, observed supervoids extending hundreds of millions of light-years, might be the products of multiple mergers throughout cosmic history. These giants could have formed when several smaller voids merged in a chain reaction, each merger creating a larger system more likely to absorb neighbors. Statistical analyses of void-size distributions search for evidence of this runaway merger scenario, looking for breaks or power law slopes that would indicate a transition from single-generation voids to merger products. Void mergers might also leave signatures in the cosmic microwave background through the integrated Sachs-Wolf effect. As two voids merge, the combined gravitational potential deepens, and CMB photons passing through must climb out of a deeper potential well than they fell into initially. This creates a time-dependent gravitational potential, precisely the condition needed for ISW effect, potentially creating cold spots in the CMB aligned with merging void systems. Detecting such correlations would require precise timing of mergers and carefully controlling for other ISW sources, but the signal might be present in data. The future of void science. As astronomical capabilities expand and theoretical understanding deepens, cosmic void research stands poised for transformative advances. Several emerging technologies and approaches promise to reveal void properties inaccessible to current methods, while refined theoretical models will enable new tests of fundamental physics using voids as laboratories. The next decade will likely see voids transition from curiosities to precision cosmological probes, rivaling or exceeding more traditional methods. Next-generation spectroscopic surveys represent the most immediate advance. Projects like DESI, Foremost, and the spectroscopic component of Euclid will measure redshifts for tens of millions of galaxies, mapping cosmic structure with unprecedented completeness. These surveys will identify hundreds of thousands of voids across vast volumes and wide redshift ranges, enabling statistical studies currently impossible. With such large void samples, researchers can examine how void properties vary with environment, cosmic epoch, and large-scale structure context, testing evolution models, and searching for rare or unusual void systems. Radio astronomy's next generation will revolutionize void gas studies. The square-kilometre array, when completed, will detect neutral hydrogen across cosmic time with sensitivity exceeding current instruments by orders of magnitude. SKA could directly map the 21 centimetre emission from cold hydrogen in void interiors, finally revealing whether the cold gas clouds predicted by theory actually exist. It might even detect the cosmic web's faint filamentary network within voids through stacked observations combining signals from many systems. Fast radio burst observations are emerging as powerful probes of ionized gas in voids and the intergalactic medium generally. As FRB samples grow into the thousands and host galaxies are identified, dispersion measurements will map the distribution of free electrons throughout cosmic structure. Comparing dispersion measures for FRBs passing through voids versus filaments will directly measure electron density contrasts, potentially solving the missing baryon problem and revealing whether substantial ionized gas resides in void interiors. Gravitational wave astronomy might contribute unexpected insights to void science. Inspiraling black holes and neutron star binaries produce gravitational waves that propagate through cosmic structure on their way to Earth. The waves' properties, frequency, amplitude, and polarization could be subtly affected by the gravitational potentials they traverse, including negative potentials from voids. While current detectors lack the sensitivity to detect such effects, future observatories like LISA, Laser Interferometer Space Antenna, might measure gravitational lensing of gravitational waves by cosmic structure, including possible delensing by voids. Machine learning applications are transforming void identification and characterization. Neural networks can be trained to recognize voids in galaxy distributions, potentially outperforming traditional algorithms and finding voids missed by human-designed methods. Machine learning can also identify correlations between void properties and cosmological parameters too complex for humans to specify, potentially revealing new void-based cosmological probes. These techniques are particularly valuable for analyzing the enormous datasets from next-generation surveys, where billions of galaxies must be processed to extract void catalogs. Theoretical advances will match observational progress. Improved simulations incorporating baryonic physics, gas dynamics, star formation, feedback processes will predict void properties more accurately than current dark matter-only simulations. These predictions will enable more stringent tests of galaxy formation models and feedback prescriptions. Simulations exploring alternative dark matter models, modified gravity theories, and exotic physics will generate predictions for how voids differ in these scenarios compared to standard models, guiding observers toward the most discriminating measurements. Cross-correlation studies combining void catalogs with other datasets will unlock new applications. Correlating voids with weak gravitational lensing maps reveals void mass profiles and tests gravity. Combining with X-ray or Sunyaev-Zeldovich effect maps probes hot gas in and around voids. Correlations with the cosmic microwave background test integrated Sachs-Wolf predictions and search for anomalous signals that might indicate new physics. Each correlation provides independent constraints on void properties and cosmological parameters. The study of void dynamics, how matter flows within and around voids, will advance through peculiar velocity surveys measuring galaxy motions directly rather than inferring them from positions. Projects like Wallaby, using neutral hydrogen velocities, and optical surveys employing the fundamental plane or Tully-Fisher relations will map velocity fields around thousands of voids. These data will test whether void expansion matches theoretical predictions, reveal systematic flows that might indicate nearby massive structures, and constrain modified gravity theories that predict different velocity-density relationships than general relativity. Void studies might even contribute to resolving current tensions in cosmology. The Hubble constant, measured from the local universe, disagrees with the value inferred from the cosmic microwave background, a discrepancy called the Hubble tension. Some explanations involve local underdensities or peculiar velocity flows affecting distance ladder calibrations. If our local group resides near a substantial void, this could bias local measurements. Careful mapping of voids in our cosmic neighborhood and measuring their effect on local expansion rates might help resolve this tension or rule out local void explanations. Looking further ahead, voids might become sites for exotic physics searches. Their low matter density and minimal electromagnetic contamination make them ideal environments for detecting weakly interacting particles or fields. Future gamma-ray observatories might search voids for dark matter annihilation signals in some models. Even small dark matter densities could produce detectable gamma rays if annihilation rates are high enough. Similarly, searches for axion-like particles could focus on voids where background noise from astrophysical sources is minimized. The ultimate goal of void science isn't just cataloging empty spaces, but using them to understand cosmic evolution, test fundamental physics, and probe the universe's composition and fate. Voids represent experiments nature performed for us, regions where we can observe gravity, dark matter, and cosmic expansion operating in their purest forms, minimally contaminated by the complex baryonic physics dominating galaxy clusters and filaments. As our ability to study these regions improves, voids will transition from cosmic afterthoughts to essential tools for understanding the universe at its largest and most fundamental scales. The emptiness, it turns out, is where some of the universe's deepest secrets hide.